Welcome to Math 31. This is a lesson on transformations of functions. This is actually a review topic for Math 30 Pure or equivalent course that you might have taken. So I'm not going to spend a lot of time on it, go through it in a lesson or two. And it's of some significance, although not the most important thing that we do. It's basically examining and analyzing the changes to a graph according to certain changes to the equation. So if we took any function f at x, y equal f at x, y equal a, f at b, x minus h plus k represents a transformation of y equal f at x, of the original. And transformation refers to a stretch, either vertically or horizontally, a reflection over the x-axis, the y-axis, or the y equal x line, and then also a translation, which means you just move the graph left, right, up, or down. Now, these parameters, or these letters, are what tell us what's going on with it. Now, so I'm going to go through this quickly, so hopefully you know what I'm talking about. A represents a vertical stretch. So I'll write that just as VS, vertical stretch, by a factor of A. So a vertical stretch means that it's being pulled up, down, or pushed together, but always vertically. The B value is the horizontal stretch factor, but it's a horizontal stretch factor by a factor of 1 over B. The reciprocal. This is a horizontal translation, which I'll indicate HT, of H units. And K is a vertical translation of K units. A couple other things to be aware of. That if A is negative, so if A is less than 0, then there's a reflection, the function is reflected in the x-axis. If B is negative, then we have a reflection in the y-axis. So that's everything. That's the entire 30 pure unit in transformations, pretty much right there. Now, to get good at these, or at least good enough at these, we will have to go into take a look at a few examples. Now, I should point out first, if you are taking 30 pure recently, they're a little more specific about things. For example, that vertical stretch by a factor of A, they would also say it is a vertical stretch by a factor of A about the x-axis. And I'm not going to bother. And the same thing with a horizontal stretch. There we would say that it's about the y-axis. In Math 30 Pure, you're always aware of which line that you're stretching it over. But in this course, we will assume that the stretches will always take place over the x or the y-axis, unless indicated otherwise. Now, to describe the following functions in terms of transformations, we start off with this quadratic graph. Y equal x squared is the original, untransformed quadratic. And then we have taken it and we have applied these few values. Now, the negative indicates a reflection in the x-axis. And then the plus 1 indicates a horizontal translation of 1 unit left. So I'm just going to write it like that. Nice and simple notation. Now, incidentally, we usually do these in an order of operations when we're graphing it, and the order of operations, unless stated otherwise, and it can get more sophisticated. So if you're taking 30 pure, you will look at it in a more complicated way, but RST is the way a lot of people do it. Reflections, stretches, and transformations. So make a note of that. So that means that if we're given a graph like this, when we are to draw it or sketch it, we will reflect it first, then do the stretches, and finally translate, unless indicated otherwise. So let's take a look. This is your original function, y is equal to x squared, untransformed. And then, if we take a look at the graph after it has been transformed, we get this. So you notice that it has been reflected in the x-axis, so it's a mirror image of it down, so it's flipped over basically, and then the 1 unit over to the left. So that does give us y is equal to negative x plus 1 squared. Let's do another one. Y is equal to 2 x minus 3, square root of x minus 3 plus 5, compared to y is equal to the square root of x, the original untransformed square root function. Now, this 2 indicates a vertical stretch by a factor of 2. And at any point, pause me and do it yourself, and then compare the answer. That's a good way to do it. Can't do that in a regular class. So vertical stretch times 2, then this is a horizontal translation of 3 units right. Got to be careful because the x minus 3, one way to think of it, of course, is the sign is always opposite for horizontal translations. The other way is because the form is x minus h, in this case, h is equal to negative 3. So x minus negative 3 would, of course, be written as x plus 3. And then the vertical translation of 5 units up. So it is going the direction it says it is. One way that people think of it, too, is when the y variable is isolated, the vertical transformations are always honest. The horizontal ones are always dishonest, meaning that the vertical, if it says a 2 there, in the vertical stretch position, A, then there is a vertical stretch by that number. Now let's take a look at this graph and see what we can do. Now this is the original. I'm going to rough it in first. So we vertically stretch it by a factor of 2, so that means that it's going to be, every y coordinate is going to be doubled. So it's going to look like this. And then all we do is we pick it up and move it 1, 2, 3 units over to the right, and then 1, 2, 3, 4, 5 up. So your graph is going to look like this. You know, rough, but fairly accurate. And then there it is on the graph. So they did that's a better job, obviously, but that's what it would look like. Let's try a few more. Now this one's got some problems. It's an absolute value function to start with. Oops. But one thing, we must isolate b, or isolate the x, which means factor out negative 3. So in other words, express in form y is equal to f at b x minus h. So you always need to get that b taken out of it. Otherwise, you can do nothing. Or, well, okay, let me back that up. You can do something. You could even get the horizontal stretch factor right, but you will blow the vertical or the horizontal translation. So we factor the negative 3 out. So we divide both terms by negative 3, and we then get x minus 3, such as this. And now, by inspection, because there's a negative there, we have a reflection in the y-axis. Now that in itself is interesting, and we'll return to it. But by the book, that's a reflection in the y-axis. The 3 is a horizontal stretch, but by a factor of 1/3, the reciprocal. So you have to recall that the b value that affects the horizontal stretch will have to take the reciprocal of it. And then a horizontal translation of 3 units to the right. So let's put this on the graph, take a look at it. Here's the original. And when we do the reflection in the y-axis, you'll note that nothing happens. It's already perfectly symmetric about the y-axis. And in fact, if you look at the equation, if we go back to that, we can see it because the absolute value will make this positive. So in fact, we could take the absolute value of -3 and put it outside the absolute value. So really, this is the same equation, which changes things a little bit, or at least how we interpret it. Now the next thing is we have this horizontal stretch by a factor of 1/3. Now that means that it's been horizontally compressed, if you like, so move towards the y-axis by a factor of 3. So every point will be, every x-coordinate would be multiplied by 1/3. So this point, for example, where x is 6, will change to x is 2. So our graph is going to be a little bit steeper as a result. Oops. I'm just roughing it in. We'll get a good look at it later. And then finally, we pick this graph up and move it over 1, 2, 3 units to the right. So that's going to be the graph ultimately looking like that. So let's take a look at that next one. Here's what we get. And that's basically right. So it's been horizontally stretched by a factor of 1/3, and then it has been, well, reflected first and then translated 3 over. Now another observation that you probably would make would be that this could have been written as a vertical stretch by a factor of 3. And that's typically the case, because a horizontal compression that is moving it towards the y-axis is really the same thing as stretching it or expanding it vertically. Maybe not by the same factor, but in terms of direction it would have the same effect, in terms of like making the graph narrower or wider. So you actually do have that choice. You can call it a vertical stretch or a horizontal stretch by a different factor. It's kind of interesting. Now the next one is more complicated still. This is an exponential function because we're starting with y is equal to 3 to the x. And exponential graphs are a little tough to work with, but I think we can do the work on the math on this, and we can somewhat make it manageable. We have to divide by -2 because the y will need to be isolated. And that can only be written, dividing by -2 is the same thing as multiplying by -1/2. And we want to keep it in that form because now we can identify the vertical stretch better. And then the base of 3 stays as. You don't multiply it by 1/2 because we have the exponent. Can't be multiplied in. Then we factor out the negative on top, and that gives us x minus 2. So we need to do that, just like we did in the previous question, to get the x value isolated. And then we also have to make sure dividing that 8 by -2 gives us -4. So this is what the equation is going to look like. So the negative in front indicates a reflection in the x-axis. The 1/2 is a vertical stretch by a factor of 1/2. The 3 is not a transformation. The 3 is part of the original equation. And then the negative up there gives us a reflection in the y-axis. And then a horizontal translation of 2 units to the right. And a vertical translation of 4 units down. And that's everything. So let's take a look at the graph. Now, I've only got the original drawn in, But let's see what we can do with it. We do the reflections first. So here's our exponential function with a y-intercept of 1. And if we reflect this one in the, say, the x-axis first, it's going to look like this. Oops. It's going to have a intercept of -1. And then if you reflect that one in the y-axis, this is going to be a little messy, but I guess we'll be okay. It's going to be a mirror image in the y. Then, when you vertically stretch it by that factor of 1/2, it means it's going to now have a y-intercept of -1/2, because we multiply all y coordinates by -1/2. So that's going to make the graph a little less steep. And then finally, we move it 2 units over to the right. So we move it 2 there and 4 down. And then draw it in as best you can. So it's not beautiful, but I think that's what it's going to be like. Now on your calculator, if you entered it in, I didn't bring up the calculator graph, just enter -0.5 times 3 to the exponent. Now I'm going to enter it in as -x plus 2 before I factor the negative out, just for ease. Because if you did that other version of it, you'd have to put an extra bracket up, and then -4. And you should get something similar. Exponential graphs, it's really hard to draw them in terms of their steepness very well, but the graph should be pretty close. So you can actually do pretty good work by graphing with transformations. The difficulty is that it really only works on familiar graphs. You have to know where to start from. You need to know what the base graph looks like and then walk off all the transformations. So it's not that helpful if you don't know what the original looks like. Let's do one more. Here we take a trigonometric one, a sinusoidal wave. And as before, we need to factor out whatever coefficient is with the x variable. So this is y is equal to the cosine. We factor the 3 out, and then we get x minus pi over 3, and then plus 1. This 3 indicates a horizontal stretch by a factor of 1/3, the reciprocal. The pi over 3 indicates a horizontal translation. If you've taken your trig recently, you'd know that we call that a phase shift. But I'll call it just a horizontal translation of pi over 3 to the right. And then a vertical translation of 1 unit up. And I think I've got all the information there. So let's take a look at that graph. There's the original. It has a trigonometric scale. And if we take a look at the transform graph, might be able to make sense of it. Here's cos x there. This is the other graph. You'll notice that it's a little tough to see what's going on, but we have compressed it horizontally. It's cycling much quicker now. When the period would be much less. Like if you measured the distance of a full rotation, would be actually by a factor of 1/3. It has been translated up. You can see that the center of the graph is 1 unit up from where it should be. And what else have we done? We have, interestingly, we've translated it to the right, but by pi over 3, because this point there corresponds to this point, right? So it has been moved over to the right, but it almost looks like we're back in phase again, if you want to use that sort of language for it. So it could almost be, it could in fact be described as a reflection in the x-axis as well. Those of you who've taken the trig before will remember that you have an infinite number of possibilities for your sinusoidal waves in terms of like the phase shift. You could call them a reflection. You could translate it left instead of right. All sorts of choices. You just don't know. So I'll leave it at that. And then the next lesson will be the final one that we do on function review. So thank you.